Since with the holidays, we're running out of days, actually. All right. So obviously, we're continuing talking here with gases. Any questions on sort of partial pressures that we talked about there? Okay. So to continue on, we're going to then talk about the kinetic molecular theory of gases. And these are some of the points that we kind of touched upon a little bit as we were going through this chapter. Some of the main parts of the kinetic molecular theory of gases is each gas is composed of molecules that are separated by distances that are greater than their own dimensions. And because of that, as I talked about previously, we sort of believe in sort of the gas volume itself as not being super important compared to the container it is in, and the volume of the gas is negligible. And this again is one of those parts that really makes something an ideal gas, is that idea that when we talk about sort of the volume, we oftentimes refer to, if you think about sort of problems that maybe you've come across, a lot of times they refer really to the volume of the container the gas is in rather than the volume of the gas itself, as it is really negligible, the actual volume of the gas. That is because they kind of fill the container uniformly as they're flying around. And so, for example, again, if you put like a marble or something into a trash can or big trash can, that little marble sort of volume compared to the volume of the entire trash can is pretty negligible. Pretty much the trash can's volume is going to be really the big volume there. And again, that is one of the sort of tenets that makes something an ideal gas when we talk about sort of ideal conditions. Gas molecules are constantly in motion in random directions. They do frequently collide with one another. These collisions among molecules are perfectly elastic. Again, they're just going to kind of bounce off of each other, no big deal. Number three here is really the second part of this that makes, again, something an ideal gas. And that is that gas molecules exert neither attractive nor repulsive type forces to one another. And again, that's sort of the second part of sort of what makes something an ideal gas. That is also why, again, as we talked about when we just did our calculations for partial pressures, even though we had multiple gas molecules maybe in the same container, we can almost assume that they are in there by themselves, as there's going to be no sort of significant interaction between gas molecules under ideal conditions. As we'll talk about in sort of non-ideal conditions in just a second here, you do have to sort of take that into account, the interactions between gas molecules. But in an ideal situation, which we normally deal with, we don't have to worry too much about any of those attractive forces or repulsion type forces between different gas molecules. The average kinetic energy of molecules is proportional to the temperature of gas in Kelvin. Any two gases at the same temperatures will have the same average kinetic energy. And one of the relationships, obviously, of temperature and sort of speed, as we'll talk about. Typically, again, if you increase the temperature, gas molecules will kind of fly around a lot faster as they have a lot more energy associated with them. And if you lower the temperature, the overall energy is decreasing. So we will see a slowing down of our gas molecules as they lose that energy. So some of the relationships that we saw as we went through the chapter, Boyle's law, again, the pressure is proportional to the collision rate, and the pressure is proportional to 1 over the volume. And that was sort of our inverse relationship. As one goes up, the other goes down. Charles' law, again, with Charles' law, as we talked about, we do see the volume adjust with increasing temperature and decreasing temperature. And remember, in Charles' law situation, that is what allows it to sort of keep constant pressure, is that adjustment of the volume to keep the number of collisions intact, are sort of in the same place, and thus the pressure doesn't go crazy. And that's different than what we saw with Guy-Lussac's law, where we didn't have the volume that could adjust. So when we did increase the temperature or lower the temperature, we saw a direct relationship to the pressure being changed as well. Avogadro's law, as we talked about, pressure is proportional to the number of moles, and sort of the moles and the volume are related to each other. When we talk about partial pressures as we did in our calculations, again, we could use that sort of idea that there's going to be really no attraction or repulsion forces between molecules. So really, whatever other gases are in that mixture is not going to have any bearing on the gas you're looking at. So again, we could almost, in this ideal situation, just think of them as there is really no other gas in there with them. They're in there alone. And again, that's what it allows us, as we talked about, to sort of just individually do ideal gas laws for each of those things. The next thing we're going to talk about is sort of the study of gas speed. And you could have, obviously, an apparatus such as this to detect our gas molecules and how fast they're moving. Slower gas molecules will hit sort of the container there. Faster ones will hit it faster on the detector. And when we look at the same gas molecule at different temperatures, what we see is as we increase the temperature here, as we went from 100 to 300 to 700, the speed of the nitrogen gas did increase. So the bulk of the molecules are here, and we do see an increase in the speed as we increase the temperature. So again, what we would expect is increase in temperature should make that gas molecule move faster. And obviously lowering the temperature should do the opposite effect. If we lower the temperature, which would be going in this direction, we will actually see a decrease in the gas speed. Now, if we keep the temperature constant, but look at different gases, we actually will see the relationship that we were talking about a second ago. Here's chlorine, and we see its average speed is about there. And then we got nitrogen, which is about there. And we got helium, which is about there. And what we see the difference between three of these, or these three gas molecules, is the molar mass. And what we see is the lightest molar mass has a greater molecular speed than a heavier chlorine over here, which is about 70 versus 4. And we have a much slower moving gas molecules because it is heavier. You could actually calculate the speed, and that is what this equation is here. This is RMS, that is the root mean square velocity. So that is the root mean square velocity is equal to the square root of 3RT over the molar mass. Now, the R in this particular case is not the R that we use in the ideal gas law. This is the R that actually involves energy, 8.314 joules per Kelvin per mole. So it is a different gas constant than the one that we use in the ideal gas law. Now, one of the relationships that's important here is one that maybe you remember, but if not, we saw it way back when, I think. A joule is equal to a kilogram meter squared second squared. So a joule is equal to kilogram meter squared second squared. And that's important because when you calculate the root mean square using this formula, you will end up in meters per second as the units that you end up with. Temperature here does need to be in Kelvin. Now, when we look at the gas constant, that 8.314 joules can be substituted in for kilograms meter squared second squared, and that's basically the joule part of the units. That would be obviously divided by Kelvin and divided by mole. So what that means, and the importance of using this equation, is molar mass we normally calculate in grams per mole, but it is not going to cancel out correctly with that joule kilograms. So you actually need to convert the molar mass to kilograms per mole so that everything works out right. The good news is the value of R is the same, just the units are changed. And that is how we get to sort of our meters per second as our final units. So if we look at, there we go. If we take a look at just the units part here, get rid of some of this here. So if we take a peek at just the units inside the square root, R is basically kilograms meters squared divided by second squared, Kelvin and mole. And again, this part of it is the joules part of it, along with the guy on the bottom. And we're going to times it by the temperature in Kelvin and divide it by the molar mass in kilograms per mole. So if we look at our units here, Kelvin will cancel, moles will cancel, kilograms will cancel, and you'll basically end up with the square root of meters squared over second squared, and that is how we get to meters per second in this particular case. So like I said, the good news is really the R value doesn't change. It's just kind of remembering this relationship for a joule. And hopefully if you remember that, you also remember that, again, the molar mass here does need to be in kilograms, not grams. Otherwise, you're going to be off by a factor of 1,000. So that's a really important sort of thing to keep in mind there. Any questions on that there? So if we wanted to calculate, for example, the root mean square here for, let's just do our helium, which is 4.003 grams per mole, and our neon, which is 2018 grams per mole at 27 degrees Celsius. So why don't you take a moment and calculate that? We're looking for the root mean square for helium and also for neon. Yeah. All right, so take a moment, see what you come up with there. You equal the square root of 3RT over the molar mass. So obviously we have molar masses from the periodic table. It's gas law, so obviously we're going to convert to Kelvin here. So we got our 300 Kelvin in this case. And again, remember here that the R is not the one that we use in the ideal gas law. So again, it is the one that has the energy units associated with it, which hopefully you also remember is it actually is this sort of relationship here, the kilograms, meters squared, second squared. And that will help you remember that you do need to convert these guys also into Kelvin, not Kelvin, but into kilograms in this case. So if we do that, basically divide this by 1,000. So divide by 1,000 there. And that's going to give us 0.004003 kilograms per mole. Same thing here, 0.02018 kilograms per mole. So now that we got everybody in kind of the right units here, we'll go for our first one, helium. We'll go 3 times our R, kilograms, meters squared, second squared, Kelvin, mole, times our temperature, which is 300 Kelvin, divided once again here by our molar mass in kilograms per mole. Once again, that's going to allow everything to cancel out correctly. Kilograms cancel, Kelvin cancel, moles cancel. Leaves us once again just meters squared, second squared underneath the square root there. So 3 times 8.314 times 300 divided by 0.004003. And don't forget to take the square root of it. Going to get us something like 1,367 meters per second is the root mean velocity, root mean square velocity there of helium. So it's moving pretty quick. Let's take a look and see how our neon is doing. So if we take our root mean square velocity, and once again, going to go 3 times 8.314 kilograms, meters squared, second squared, Kelvin, and mole. Our 300 Kelvin divided here again by our molar mass in kilograms per mole. So everything properly cancels. Going to get us here 3 times 8.314 times 300 divided by 0.0201. A little square root action. Going to hit us about 609 meters per second is the root square mean velocity of neon. First off, any questions on the calculation? So two important things to remember with this equation: kilograms for the molar mass, and R was the 8.314 version. This is actually the conditions we did earlier on that problem, that partial pressure problem, where we saw that helium had a partial pressure of 12.4 versus the partial pressure of, I think it was 2.4 there for our slower moving neon. You can see it is moving about twice as slow, right, as helium is flying around. Helium's flying around about 3,000 miles per hour, and neon's only moving about 1,300 miles per hour, right? So kind of moving really slow in that sense. So again, because of that vastness here and the speed of helium, that is why in that previous problem we saw a much greater partial pressure as a result of helium's contribution, because it's moving much, much faster, twice as fast, basically. Yeah. Any questions on that there? Next thing we're going to talk about is gas diffusion. So gas diffusion is the gradual mixture of molecules of one gas with another one based on their kinetic properties. So as we've been talking about, clearly we know that these slower moving gas molecule is going to be the heavier here. So if you pop open a bottle of HCl and ammonia, hopefully you're in a fume hood, you're going to see our faster moving ammonia molecules move this way, much faster than our slower, dramatically drawn here, moving HCl molecules trying to make its way out of the bottle. And that's why when we see them mix to make our friend ammonium chloride, which is that white sort of cloud there, we see the mixing happening closer to the slower moving HCl bottle. And again, our ammonia moving much faster is going to get over there quicker and start mixing with the slower moving HCl bottle there. You can actually calculate these things. These are rates of how they're moving, and these are the molar masses. And these molar masses can be grams per mole. Since we're not using R in this case, the gas constant, we don't have to worry about kilograms. And obviously, this would be the rate of our first gas molar mass. And obviously, this guy here would be, goes with that guy. So obviously, the rates, the molar masses should line up in terms of twos and ones if you were to do it. So gas diffusion is that gradual mixing. Again, faster molecule going to beat to the punch there and start mixing with our slower moving HCl in this case. Another sort of aspect of gases is what's known as gas effusion. And gas effusion is the process by which gas under pressure will go from one compartment to the next through some type of small opening. So that's what we see here. We got this small little opening right there. So we're going to get some gas molecules popping out from the other side. And we have pretty much the same sort of formula we just saw there. Rate 1 over rate 2, or these are time it may take for that to occur. And these, again, are the rate. And that equals, once again, our molar masses here. So if we take a look at a problem here, we could use some of this information to help us figure out, maybe if we're not sure what a formula is, but we do have some effusion sort of rates given to us. So nickel forms a gas compound with a formula of NiCO something, so we're not really sure what that number is. And what is the value of X under the same conditions? We see methane effuses at 3.3 times faster than the compound. So in this case, if you want to call R1 the unknown compound, and if I call R1 the unknown compound, then M1 needs to be the molar mass, obviously, of that unknown. So they stay together. We know that R2 will be our methane, and methane in this case, it actually effuses 3.3 times faster than the unknown compound. That means 3.3 times R1, right? So it's going to go 3.3 times faster than the first rate, whatever that first rate may be. We do definitely know, hopefully, the molar mass of methane. We did it the other day, 1604, I hope. That is what you got when you did your calculation, hopefully. And we could use this calculation to help us figure out, first off, the molar mass of the unknown compound. So let's pop our numbers in and see what we end up with here. So R1 divided by R2, which is basically 3.3 R1, equals the square root of 1604 grams per mole divided by our kind of unknown molar mass. So although I don't know what R1 is, I do know that they're going to cancel each other out. And that is going to give me 1 over 3.3 is equal to the square root of 1604 grams per mole divided by M1. To get rid of the square root, we are going to square both sides. So we're going to do a little square of both sides. And if we square both sides, we'll take 1 divided by 3.3 and then square it. That is going to get us, I'll come over here, I think, 0.091827 equals 16.04 grams per mole divided by M1. These two guys are basically going to switch places. You're going to multiply the M1 to the other side and divide that guy back over, and you'll end up with M1 is equal to 16.04 grams per mole divided by 0.091827. And that's going to give us our molar mass of our unknown compound, which will be, I don't know, we'll call it 174.7 grams per mole. First off, any questions on that calculation? Now that we actually know the molar mass of this compound, that can be helpful for us figuring out maybe what the formula is. So if we come now to our formula, what we know about our formula is a couple of things. We know that this entire formula here is going to equal a molar mass of what we just calculated. So this guy is going to equal 174.7 grams per mole. The one thing that we know for sure from this formula is it contains 1 nickel, right? So we go to the periodic table and find nickel. It's like 5869 maybe. So if I subtract 58.69 from it, which is our nickel that I know for sure is there, that will then leave me a net of molar mass of, it's like maybe we'll call it 116, right? 116 grams per mole. Now, what do I know about what's in the parentheses? So what's in the parentheses is 1 carbon at 12.01. And I have 1 oxygen at 16 grams per mole. So I know each of those parenthesis units represents in terms of mass 2801 grams per mole. And that's what each of these kind of CO units represent. So that is the rest of the mass. So if I take the 116 and divide it by 2801, we will end up with approximately 4.1, which is close enough to 4. So we should have about 4 of those CO units. And our proper formula in this case should be NoCO4 in this case, yeah. So we could use this formula here like we did to get the molar mass of that unknown. And we could subtract off the molar mass. What we do know is definitely there, which is nickel. And then obviously what's left is just those CO units and how many of them we sort of have. Any questions on that? So clearly, this is sort of an extension of the calculating the molar mass. You also, if you knew 2 molar masses, you could calculate how much the rate of one of the gases is versus the other in terms of their effusion. Any questions on that there? Okay, gas effusion, gas diffusion. All right, the last thing we're going to talk about in the gas chapter here is actually deviations from the ideal behavior. So everything that we've sort of talked about up to this point is ideal gases. And as we talked about, what makes something an ideal gas, again, is the idea that we don't have to worry about the volume of the gas molecule itself. It is negligible compared to the volume. And we don't have to worry about any type of attracted or repulsion type forces. And that frees us up to use PV equals nRT, which is kind of a very universal sort of gas law. You could use it for any type of conditions. You could use it for any gas. It's not specific for a specific gas or anything like that. But what happens when we start to deviate from ideal conditions, and when we start to get pretty giant pressures going on here, some pretty big pressures, we start to see a lot of deviation here from the ideal situation or conditions. In an ideal situation, that ratio of moles will basically be 1 all the way across there. But as we hit really, really large pressures, and as we will see low temperatures, we do have to start taking into account the attraction and repulsive forces that occur. And we also have to take into account the volume of the gas itself. So under non-ideal conditions, which is what sometimes people refer to this as non-ideal, or some people refer to these conditions as real gases, unlike the fake gases we've been talking about. These are real gases. They will have to take those things into consideration. So as we talked about, the no attraction between gas molecules do not take up space based on the kinetic molecular theory, but real gases do not behave ideally when we have these conditions happening, high pressure or low temperature. So if we just think about a couple of things, right? If I have a high pressure, we know something about the volume is going to be really, really small. So that basically means at high pressures, you have a very small volume. And now I would say you have a lot of gas molecules near each other for a very long period of time and in a very small space. What happens with that is because of that, remember earlier I mentioned that if I threw a marble into a trash can, the volume of the marble is not going to be all that big versus the volume of the trash can. Now, if I take that trash can over there and throw a basketball in there, that volume of the basketball is going to be significant compared to the volume of the trash can, right? It's taking up a pretty good amount of space and stuff like that. And that's what's going to start happening in this situation because of those really high pressures. In addition, if you think about low temperature, as we talked about, that means my gas molecules are now traveling quite slow, right? And they're moving dramatically drawn here is quite slow. And that means that as gas molecules pass each other in the night there, they're going to be near each other for a much longer period of time because they are no longer just zipping past each other. They're just kind of slowly now moving past each other. So they'll be in contact with each other for a much longer period of time, which brings into play, as we will see, interactions that could happen between gas molecules because they're just not zipping by each other. They're now going to definitely be affected by who is near them. So at lower temperatures and pressures, the assumptions are not valid, and the molar volume of a gas does deviate from an ideal situation. The molar volume of a gas is that 22.414 number that we talked about, like at STP. 1 mole of any gas is that. So because real molecules do take up space, their molar volume of a real gas is actually larger than what was predicted by the gas law at high pressures. So you could start to see in an ideal situation, this is what our kind of molar volume should be. And in a real gas situation, we start to see a pretty good deviation, especially as we start increasing that pressure. And again, as that's sort of my basketball example there, as the pressure gets bigger, you throw a basketball in that trash can, and it's kind of taking up a pretty good volume of that trash can, right? So you can no longer ignore it, as opposed to in an ideal situation, you had a marble in that trash can and you could still kind of see everything going on in the trash can, right? It's not taking up a big amount of that volume. So the effect on the molecular volume is at high pressures, the amount of space occupied by molecules is significant to the total volume. And the molecular volume of a real gas is larger, as we saw there. So our good friend van der Waals, who did a lot of work with kind of how molecules interact with one another, he modified the ideal gas law to take this into account. And one of his two sort of correction constants, one of them is known as B. This is the van der Waals constant. And it is specific for specific gases. So there's a table where you can look up van der Waals constants, A and B, and you have to look it up based on the gas that you're dealing with. It will be different for different gases. So instead of just a regular old PV volume in our ideal gas law, we start to get some scarier looking stuff happening here. nRT over P plus N times B here. All these guys are still the same values that we use in the ideal gas law. They're all moles. That is the 0.08206 gas constant, temperature in Kelvin, pressure in atmospheres. B, once again, is a constant value that you look up based on the gas in the table. Now, the other sort of effect is at low temperatures. As I mentioned before, the gas molecules are no longer just zooming past each other. They are definitely going to be near each other for a much longer period of time. And that is definitely going to cause some interaction to occur. And again, here we see a real gas versus an ideal gas. We start to see some separation happening when we drop down to some low temperatures here. So the molar volume of a real gas is smaller under these low temperature conditions. And van der Waals also had a correction value for that for the ideal gas law, and that is the A constant. Once again, much like the B constant, these are values you would look up in a table, and they are specific, again, for different gas molecules. And this takes into account the intermolecular attraction, the repulsion forces, and the attraction forces that occurs. And we have this sort of correction value that occurs in here based on van der Waals. Now, why is attractive forces and repulsion forces going to affect things? Well, if you think about just a gas molecule in an ideal situation, even though there are gas molecules around it, frankly, they're not going to be attracted or repulsed. So, frankly, it is free to just jam into that wall with no repercussions. But now, if you say, for example, this gas molecule here in real conditions has some attraction to these other gas molecules, as it's making its way towards that wall, it will actually perhaps feel some back pull away from the wall and going to slow it down perhaps, right? And it's going to slow down perhaps the number of collisions and have an effect on the pressure that you would associate with that, because it's no longer just free to move around and collide. It will have some drag from those other molecules. It may also perhaps increase the pressure a little bit if it comes across a molecule where it doesn't want to be around and repulses away from it. It may actually jet away from it and cause a little bit more collisions to occur. So this is what is known as the van der Waals equation. It is the scary looking version of the ideal gas law, and it is used to correct for the pressure and also correct for the volume here. And this is, again, a table similar to one in your book where you would look up your van der Waals constants A and B. You would plug and chug into here and solve it like a normal equation. It is obviously much scarier looking than the ideal gas law here, which is just PV equals nRT. So one of the things that we oftentimes think about is we kind of always, a lot of times, will deal with sort of ideal conditions. As I mentioned before, this is more of a universal gas law. You can use it for any gas you want. This is really more of a specific gas law, obviously for high temperatures or high pressures or low temperatures. And it's more specific because now you got to, every gas is different in terms of their values of van der Waals constants. So it's not as universal. So why do we normally, in a lot of cases, always sort of assume ideal conditions in most cases? If we go back to that sort of first graph that we saw here, where that was that thing there, right about here. Get rid of those guys there. We'll just get rid of all the writing. If we think about normal sort of conditions of pressures and temperatures, right? Normal pressure and temperature, is like 273 plus like 25, so like 298. And normal pressures is about 1 atmosphere, right? So if we take a look at where 1 atmosphere would be on this graph, it's pretty much there, right? Even if we were well above 1 atmosphere, we're not deviating too much at this point in terms of ideal conditions, even though there's a little bit, right? You need to start getting into some serious way above 1 atmosphere pressures, right? Into the hundreds or so to start to see some significant deviation, and that's almost 100 times normal pressure. And under normal conditions, we don't really see that much pressure. So we usually will oftentimes use ideal gas law and assume ideal behavior, because even at the very beginning, you could go pretty well above 1 atmosphere and still be semi-ideal in terms of the conditions. But again, if you start jumping some pretty big pressures, you get some significant deviation starting to happen from ideal conditions. So that's why in most cases we kind of roll with ideal conditions, because you would need that's kind of really significant amount of pressure and really low temperatures to sort of see some big deviation from an ideal situation. Any questions on that there? That is chapter 8. Yay. All right. Like I said, we're going to do a little bit of chapter 9 because, we got like 3 days left and 3 chapters to go. So that worked out nice, I think, with 9 here. I'm going to talk about the liquid state, and we'll do a little bit of this here while we're going. All right. So one of the things we're going to talk about here is, speaking of van der Waals, how molecules interact with each other, and how one molecule interacts with another molecule is what is known as intermolecular forces. So intermolecular forces is the forces that hold one entire molecule together with another, basically. The nice thing about intermolecular forces is they are really just a basic interaction between molecules, and it is the basic opposite attraction that occurs. So when you get two molecules near each other and they want to interact with each other, the negative side of one molecule will be attracted to the positive side of another. And that's pretty much how all intermolecular forces are. It's just basically electrostatic attraction, positive and negative side is what does that. Intermolecular forces are really important for things like melting points and boiling points. The stronger the intermolecular force, the higher the melting point and boiling point will be. And that's because, for example, if you have these two molecules here together, say in the liquid phase, and this was a really strong intermolecular force, the only way these guys can go into the gas phase is you got to break that force, right, between them. And if it's a really strong force, you're going to need a lot of energy to get those guys away from each other. And because you're going to need a lot of energy, you will result in a much higher boiling point than if these two molecules here were held together by a very weak intermolecular force. If they're held together by a really weak intermolecular force, you don't have to take a lot of energy to get them away from each other, and that's going to give you a much lower boiling point or melting point. So we would end up with a lower boiling point or melting point in this situation. So really, the stronger that intermolecular force, the higher you will see in boiling points and melting points. The other thing intermolecular forces are really important for is solubility and how molecules interact with each other. So as we will talk about a little bit in this chapter and the next chapter, basically how molecules interact with each other and determines whether or not they will kind of mix together or interact well with one another is if they are both using a similar intermolecular force, you're going to be good. You're going to be golden. They're going to mix really well. So if you try to take something like water, which uses hydrogen bonding, and you want to mix it with something like methanol, which also can hydrogen bond, you're good to go. Those two things are going to mix all day. If you want to take water, which uses, again, hydrogen bonding, and you want to mix it with something like chlorine water, which is nonpolar, uses dispersion forces, those are very, very different intermolecular forces, and it's not going to mix at all. So they don't have a way to interact. So intermolecular forces affect things like melting points and boiling points. It also affects how molecules can either interact with each other or not interact with each other, depending on what type of forces are present. Now, intermolecular forces are different than intramolecular forces. Intramolecular forces means within the molecule. So, for example, if you took just one water molecule, the intramolecular force are those covalent bonds, those electrons being shared in this case, between the oxygen and the hydrogen on each side. And that's the intramolecular force. And again, if we had two water molecules, which, as you know, is a polar molecule, more negative on the oxygen, more positive on the hydrogen, we will get an interaction happening between the negative side of one and the positive side of another. And that, again, is an intermolecular force. Again, intramolecular forces are usually much stronger. Those are like your covalent bondings, your ionic bondings, your electrostatic attraction. And we know this just from water, as we talked about, I think, when we began the gas chapter. When you heat water, if this is water in the liquid phase, and you go to heat it, when you get to 100 degrees Celsius, what happens is you break this bond, the bond between this water molecule and this water molecule, that allows them again to go off into the gas phase, right? And you form steam, which is still water. If that was opposite and this guy here was actually weaker, when you would go to heat water, you would start breaking these bonds, which probably wouldn't be a good thing, because then you would produce some oxygen gas and hydrogen gas, and that's probably not great, as you're maybe trying to make some pasta or something there, while you're trying to cook dinner. So because they are much stronger, this whole molecule will stay together, and the actual bond between molecules will be the ones that break apart. Any questions on that there? So we're going to talk really specifically here about intermolecular forces. So these are all intermolecular forces. And again, the forces between molecule and molecule. The first type of intermolecular force is what is known as a dipole-dipole interaction. Perhaps you remember that word from bonding and our friend, the dipole moment. Yes, dipole moments occur in polar molecules. And basically what that means is overall there's unequal sharing of electrons. And what that means is in a polar molecule, no matter what you do to it, there is always a positive side and a negative side to that polar molecule. And that means that when you take one polar molecule that has always a positive and negative side, and you attach it to another polar molecule that has a positive and negative side, or two positives, you're right or wrong. Let me try that again. There we go. Maybe I get it right here. Come on, pen. You want to write. There you go. We will get our attraction that will happen here between our two sides here of our polar molecules. And this is basically dipole-dipole. Because polar molecules always has that separation of charge, they are always good to go. They're always good to interact with these guys. And they will, for example, in, say, the solid phase or the liquid phase, they will try to align themselves up in a way that maximizes the positive and negative attraction and minimizes the negatives and negatives. No matter what you do, you're always going to kind of get some negatives near negatives and positives near positives, but they actually will, for example, in like the liquid phase, just kind of keep moving around so they can find some type of arrangement which is happy for them, that maximizes more the attractive forces versus the repulsion forces. And that's what we see here. Again, it will continue to move around, maximizing attraction, and again, trying to minimize those repulsion type forces. The next type of intermolecular force is an ion dipole interaction. And this is basically what happens when we dissolve an ionic solid, say in water. As we talked about, if you take an ionic solid, you're going to get something like sodium ions and chloride ions, and they're going to get surrounded by the negative side of water, which is the oxygen, and the positive side of water, which is the hydrogen in this case. And that's pretty much your ion dipole interaction. Dipole coming from our polar molecule here, water, and obviously ion here. Yeah? And it's the same idea. You have a cation that's positively charged, will definitely be attracted to the negative side of the polar molecule, and our negative ion will be attracted to the positive side of the polar molecule. So again, that's ion dipole interactions. And again, that's what allows, for example, ionic compounds to be very soluble in water. That's also why ionic compounds have low solubility in nonpolar solvents, because you have a positive ion and now you have a nonpolar molecule which is essentially neutral. It has no charge, so they just sit there and kind of stare at each other. They don't really have a good way to interact with one another because there is no positive or negative side, in a sense, with our nonpolar molecule. It can, as we will talk about, create a temporary separation, but overall there's really kind of no attraction that occurs there. So let's talk a little bit about dispersion forces. And dispersion forces are the main type of force that is used for nonpolar molecules. So this is really the main force that is used between nonpolar molecules and other nonpolar molecules. Now, because nonpolar molecules are essentially neutral, it is quite problematic for them to interact because they don't have a positive side or negative side. They need something to occur to temporarily give them a positive side and negative side. So they kind of have to rely upon something happening to allow them to have that interaction that can occur. And that is what is sometimes referred to as an induced dipole. You could roll something up on a nonpolar molecule that can cause it to temporarily gain some charge separation. For example, if we took a nonpolar molecule and you rolled up a positive ion next to it, the electrons in this nonpolar molecule will temporarily be attracted to that side of the molecule because now there's a positive charge that kind of rolled up on it. And what that will create is, in this nonpolar molecule that normally doesn't have a charge, it will temporarily gain a separation of charge that it normally doesn't have. And now these guys do have a way to temporarily interact with one another. Same thing if you rolled up a polar molecule on a nonpolar. Again, you have your negative side of the polar molecule is going to make the electrons actually go that way in the nonpolar. And now you will have this polar molecule that can now interact temporarily with this nonpolar molecule because they now both have a charge. These are temporarily sort of interactions. These are very weak interactions because the nonpolar guy has no way to like maintain that forever, if you will. It can, as this molecule goes away, starts to break back to a neutral molecule, and those interactions are going to break apart. This is why, right, when you mix something like oil and vinegar salad dressing, it mixes for a bit, right? But if you leave it alone, eventually separates out. Oil being non-polar, vinegar being kind of polar. So for the short period of time, you're going to have all these kind of dispersion interactions happening. But as you leave them alone, they're going to kind of break apart, and then everybody's going to kind of separate out from one another. They can't maintain that. Also, why when you have like an oil spill in the ocean, right? The oil ends up on top floating, right? Because it can't continuously mix with the water, and it just kind of floats up on top, is not able to keep that interaction going. So dispersion forces are usually very weak type of interactions because of that. And this is one way that you could do it, inducing it with a ion, which is ion-induced dipole interaction, or a polar molecule, which is known as dipole-induced dipole interaction. Another way that this could happen is actually when you just have two nonpolar molecules near each other. It is possible, because electrons are flying around, that all the electrons in this first nonpolar molecule decide to take a vacation this way. And what's going to happen when it does that is now that first guy will have this separation of charge. And if he's still next to this guy, the electrons in this guy will decide, oh, that's cool, we'll go this way. There's like a positive charge over there. And now these two normally non-polar molecules that do not have a separation of charge have gained what is known as an instantaneous dipole, because these electrons basically went a little bit crazy, and now they have a way to temporarily interact with one another. The ease at which electrons can kind of do this is what is known as polarizability. It actually increases with molar mass. So although this is still dispersion forces here, dispersion forces actually increase with molar mass. The strength of this really weak sort of dispersion force increases with molar mass, because higher molar mass, more atoms, more electrons, more places for this to occur, and more interactions that could actually occur. So when you're comparing something, for example, in terms of boiling point, that is nonpolar and nonpolar, and you want to know which one has the greatest boiling point, it is the one usually with the more molar mass, because it'll be easier to do this kind of polarizability, and will have a stronger interaction than something with a smaller molar mass. By the way, they both will have a much lower boiling point than anybody doing dipole-dipole, because that's a much stronger interaction that could occur. Now, as I mentioned before, the dispersion forces are usually increased with molar masses because of the larger amount of electrons that are present. Dipole-induced dipole, and dispersion forces, they are sometimes referred to as van der Waals forces, which, as we just saw there with the van der Waals equation, he obviously did a lot of work with how molecules interact with each other and these intermolecular forces. And that's what we're talking about here. Instantaneous dipole, this normally non-polar guy will get a temporary separation charge, causing this guy to also get a temporary change of charge. And now they're going to have a way to interact temporarily with each other. Obviously, as these electrons go back, those interactions will kind of break apart and new ones will form, and those will break apart and new ones will form. And that's why they're very weak and temporary, because they just kind of keep breaking back and forth. That's different than what you have in a polar molecule, a dipole-dipole interaction. No matter what you do to that polar molecule, it always has a positive side and negative side. It will never go away, which means it's always good to go in terms of doing its interaction. And that's why it's much stronger than these guys, that has to rely upon something to occur to give them a charge so they can interact and make it go away. Now, the last type of intermolecular force, which is really important, is hydrogen bonding. And hydrogen bonding is a type of dipole-dipole interaction. And hydrogen bonding is a bond between hydrogen and an electronegative atom. And it needs to be something like nitrogen, oxygen, or fluorine. If you look on the periodic table, that is your big three there, right? Electronegativity increases as you go up to the right. Fluorine is the most electronegative. The reason it could hydrogen bond is when you have hydrogen bond to one of those, you create a very polar bond. If you remember, the HF bond has a difference in electronegativity of 1.9, which is almost ionic, right? So it's a really big positive negative separation within that bond, and that's what's going to allow it to interact well and make these really strong interactions. These are very strong interactions. And that is what we see with water. Water here, by the way, is directly bound to oxygen, which means it has the ability to hydrogen bond with other waters. And again, we're going to hydrogen bond through there. If I take something like NH3, can NH3 hydrogen bond? The answer is yes, because it is polar and it has a bond of hydrogen directly to nitrogen. So it can also hydrogen bond as well. Now, just because you have a hydrogen does not mean you could hydrogen bond. If you take a look at methane here, methane has a lot of hydrogens. It cannot hydrogen bond. This is a nonpolar molecule, and that hydrogen is not attached to a nitrogen, oxygen, or fluorine. So it has to be directly attached, that hydrogen that's going to participate in hydrogen bonding, to one of those three guys there, the nitrogen, oxygen, or fluorine. Any questions on that there? Now, in terms of interactions, our hydrogen bonding is really the strongest, and it is the main type of intermolecular force for polar molecules and other polar molecules that obviously has a hydrogen that is bonded directly to a nitrogen, oxygen, or fluorine. Dipole-dipole is also very strong interaction. It is also the main type of interaction for polar molecules and polar molecules that cannot hydrogen bond. So again, you could have a polar molecule that cannot hydrogen bond, but they can do dipole-dipole. So if you had something like this, that is a polar molecule. This hydrogen cannot hydrogen bond because it is not bonded to a nitrogen, oxygen, or fluorine. And dispersion forces is the weakest of all of them. And that is your main interaction of nonpolar molecules with nonpolar molecules. And this would be something like what methane would do, for example. Methane would do dispersion forces. So when we talk about sort of boiling points, melting points, anybody that can hydrogen bond should be the highest. Anybody down here should be the lowest if you're comparing between them. And again, like I said, if you're comparing just between nonpolar and nonpolar, the larger the molar mass, the stronger the dispersion force would be. Any questions on that there? Reality is everybody could use some type of dispersion forces, which is again why we get some interaction between water and something like oil, but it cannot maintain that over a long period of time. So again, you usually want to give them main type of intermolecular force that could occur. These again are really responsible for how molecules interact with each other, and again, boiling points and melting points. So if two different molecules come together and they both could hydrogen bond, they're good to go. If two molecules come together, they both could do dipole-dipole, they're good to go. If you have a molecule that does dispersion and something that does hydrogen bonding, they are not going to interact well with each other, and they're not going to really mix. Any questions on that there? All right. We got into some chapter